everyone. Today we are going to learn 5.7 changes of variables in multiple integrals. Okay, so we have a learning object here. Okay, now we had in Calculus 1 and 2 substitution method, right? For integrals. And this Calculus 3 we learned converting polar coordinate for double integration, converting cylindrical coordinate and spherical coordinate for triple integration, right? Okay, why we are doing this? Because we want to integrate easily, right? Okay, so this section is about we want to make integration simpler. So we want to make a transformation. So to make the integration simpler, so this is a transformation, this section, all right? Okay, then what is a transformation? If we have Cartesian UV plane, we never heard, right? UV plane. You transform XY plane, but this is just a general, yeah? It can be R theta plane from the R from the R theta plane transform XY plane or XY plane transformation R theta plane. So it depends on, all right? Okay, let me just read planar transformation. So planar transformation. So planar, like a plane, right? So 2D plane, XY plane. So we are using here. So planar transformation T, we are using just the first letter transformation, right? So that's the T. So T is the function that transforms a region G in one plane into region R in another plane by change of variable. All right. So we have a region G transforms region B change by another variable. In the case, UV change to XY, right? All right. Now, so we have a definition here. Definition, a transformation T. This is the function, right? G mapped to the R transforms R. We just said that earlier, right? And then defined as T of UV. So basically UV is the input. Then we get output because T is the function. We learned from the previous course, right? So function, we have input, then we get the output, right? So UV is input, we get the output. So we make a little bit fancy, right? Transformation. But basically we have a function, input and output, that's it. But then we have a restriction, one-to-one, because we learned from previous course, one-to-one, right? So when we make inverse function, we have to have a one-to-one function, right? So one-to-one function, we know that one exactly input, we get one exactly output. In other words, each input gives us the different output, right? So let me just finish the definition. One-to-one transformation if no 2 points map to the same image point. Image point is output. So think output. Okay, so I made a note there, means different input gave same output, right? Same output. Hold on 1 second. So there is no same output missing, right? So no. We cannot have the same output, right? So we have that. For your reference, I have what is one-to-one, what is not one-to-one function. So easily to think we have a straight line linear function is one-to-one, right? So one input gives a different output, and quadratic function, parabola, not one-to-one because we have a different input, but we get the same output here, right? So that's not the one-to-one. All right. Okay, just to take a look at this problem. So finding the image under T. The image, we just think output. We said earlier, right? So think output. So we have T of UV equal to XY, where X equal to U squared minus V squared, and U equal to UV. Find image of a triangle in the UV plane with the vertices 0, 0, 0, 1, 1, 1, right? So basically we want to find the transformation, right? Okay, let's do it. So we have image here. Let's just get through this one. All right. So for side A, this is side A. Then this one transforms A prime here, right? Okay, how they got that here? Let's take a look. The order pair U and V in that case, right? So this is U, V. Okay, so looking at the A. So we have a 0, 0, and then 0, 1 there, right? So we can set it up since we have a 0, 0, 0, 1, we can set up let U equal to 0, right? Since 0, 0 and 0, 1. That is UV, right? Okay, make sense? Then only V has a different value, right? Between 0 and 1 for the V. That's what they have here. V is between 0 and 1. Okay. So we have, and V is between 0 and 1. Now, let's take a look at the function. Function has x equal to u squared minus v squared. Oh, you cannot see? Sorry about that. Okay, x squared I got from here. Yeah, from the question given. X equal to u squared minus v squared. All right, then u equal to 0. Yeah, both of them 0. Then we will have 0 minus v squared, which is v squared, negative v squared, right? All right, so what about the y? Y, let's take a look y. Y equal to uv, right? So y equal to uv. Then we set up u equal to 0. And v is there, right? Which is 0. That's how we got here. Okay. Now take a look. When v equal to 0, when v equal to 0, x equal to 0, right? when v equal to 1, x equal to -1, right? Because we have a negative sign in front of the v squared, right? So that's how we got. So what about y? Y always 0, right? So we get x equal to 0, y equal to 0. Let me write down x, y. X, y. And we get -1 for the x, y equal to 0, right? That's how we got a prime there. Can you see? -1, 0, 0, 0. Yeah. All right. So same concept, b. So we have b there. B. All right. So b. Look, let's take a look. I need a space. And for b prime, so look, we have 0, 0, 1, 1, right? Then that means we can set it up u equal to v because 0, 0, 1, 1. Make sense? So let u equal to v since 0, 0, 1, 1, that is uv, right? So u and v are same, right? We can say that. Okay, now we can set it up. U is between 0 and 1, right? That's how they do. So U is between 0 and 1. Then we had, I'm going to use this one here, that question given, right? So we have this one. Let me copy. I don't have to go all the way. Come on, come on, come on, come on. Okay, let me just write. No patience for that. So x equal to u squared minus v squared. All right, then when x equal to, I'm sorry, when u equal to 0, and v equal to 0, right? So we get x equal to 0. Yeah, but then I think this is better than, okay, let me just apply this one later. This is better thinking. Okay, so since we have u equal to v, so let me using u, there is a u squared minus v, u squared. Then we can make a 0, right? And then y equal to, we have a uv. Then on the top has u times u, because u equal to v, right? Then we can have a u squared. All right, now we can apply that when x equal to 0, then y equal to 0 because u squared, then u equal to between 0 and 1. Make sense? And x equal to 0, then u equal to, we can say that this is a y actually, right? But u has 1, right? So that's how they got here, 0 and 0, 0, 0, 1. So there will be b prime. So B prime, where's B prime? B prime is here. Purple. Let me use purple. All right. So we have a 0, 0, 0, 1 there, right? Okay. Let's talk about the C, C prime. Okay, let's take a look. C has 0, 1, 1, 1, right? But then can you see that the V has same 1 there? Okay, let's use that fact. V equal to 1 and U is between 0 and 1. Make sense? All right. I hope I remember that. So for C prime, so we have a let V equal to 1. Since we have 0, 1, 1, 1, so which is UV. Yeah, V is 1, 1, right? So V equal to 1. We have this one, right? X equal to U square minus V square, Y equal to UV. So X equal to U square minus V square, U square minus V equal to 1, V equal to 1. We have that. And then Y equal to UV and V equal to 1. So U, V, which is U. Okay, now let's take a look. X equal to U square minus 1 and Y equal to U. So we can express X equal to U, which is Y square minus 1, right? So no, Y, U equal to that. So Y squared. Yeah, so X equal to, make sense? X equal to Y squared minus 1. Yeah. Okay, they say that this C prime makes it the upper half of the parabolic arc. Yeah, parabolic arc. Okay, so let's finish that. We need to set it up. U equal to 0 to 1. So U is between 0 and 1. Then X equal to, when U equal to 0, negative 1, right? We knew, right? So I don't have to show that. 0, minus 1, minus 1. And Y equal to 0, right? When U equal to 1, X equal to 0, Y equal to 1, right? Yeah. So we have negative 1, 1, and 0, 1. That's for XY transformation. Can we check that? 0, negative 1, 1. Hold on 1 second. I don't get it, huh? Let me check that. Okay, so there is a mistake, right? So when U equal to 0, X is correct, Y equal to U, so must be 0, right? So this must be 0. 0, 0. Then we have negative 1, 0, 0, 1. Let's check that. Check it out. Negative 1, 0. Negative 1, 0, 0, 1. Yeah. So that parabolic arc here, right? So it's connected C prime, right? That's how we show the transformation image of T, right? Okay, I just showed you because this is a lot of work. All right, so we're gonna do that later. Okay, now we have another definition, Jacobian. Of the C, we have a notation 1, right? So this means, okay, this C means first letter from the continuous. Normally we are using the first letter C, right? So that's the C. But then we have one on the right side hanging there, right? So one, that means first derivative exists, but then we are learning calculus 3, so that is a partial derivative exists, all right? So Jacobian of the continuous and partial derivative exists, and we have transformation T of uv equal to two functions of output is denoted by Jacobian of uv and defined by 2 by 2 determinant. So the formula is like that, right? So partial derivative, then we get multiply this way, right? So 2 by 2 determinants, we multiply this way minus this. So we have that one, right? So we are using Jacobian later on when you use the integration, all right? Okay, now we want to find the Jacobian of T of R theta equal to this is the output, right? This is the input. It's not always XY, it's not always R theta, it's not always a UV, right? It depends on function. It's given, right? So we have that. Let's do it. Okay, so we have Jacobian R theta, right? So this one gives us R theta. Yeah, we're using same input here. Okay, so look, they have a UV as input. So they're using partial derivative with respect to U, right? And then partial derivative with respect to V. So we are going to make the same form. So there will be partial derivative of x with respect to u, partial derivative y with respect to v. Oh, yeah. But then we are using r theta, right? Forgot r theta. I said earlier and then I forgot. R, sorry, theta. And in the case r, right? Theta, correct? Yeah. Okay. So there would be, I have to write down. So look, do you still remember, right? Do you still remember? This means we're looking at the x. This is x. This is y. If we make this form, right? And dr means we do derivative with respect to r. That means theta is constant, right? I don't have to write down, right? Do you want me to write down? Partial derivative. Derivative respect or that means treat theta as constant. Okay, so let's do it. Derivative with respect to r. Theta is constant, so we keep the constant, so cosine theta, right? And then same concept, we do derivative with respect to r, and then sine is constant, so we keep those constant, right? Okay, let's take a look at this one. D theta, so partial derivative respect theta, so treat r as constant. Yeah. Okay, let's take a look. We have derivative with respect to cosine theta, r is constant, so we keep the r, right? Because constants r. What's the derivative of cosine? Negative sine theta, good. Negative sine theta. Okay, now we're looking at this one. We want to partial derivative with respect to theta, then we keep the r as a constant because r is constant, right? What's the derivative of sine theta? Cosine theta, very good. Okay, now we want to make a determinant 2 by 2, right? So like this, right? So I am right-handed, so this one first, and then that, right? So we have, normally Jacobian, we have to have absolute value. So let's talk about that later. Okay, so that r cosine square theta plus and negative, yeah, negative, and then multiply this way, so r sine square theta, right? Minus, okay, that will be r cosine square theta plus r sine square theta. That will be r cosine square theta plus sine square theta. We knew this is 1, right? So there will be 1. I'm sorry, this will be r. Yeah. Okay. Let's do this one. So try second one. So we have a t of uv equal to u squared minus v squared uv. We want to find the Jacobian uv equal to, so we want to make a du dv dv. So consider this is x, this is y, right? Okay, now we want to take a look this derivative, partial derivative with respect to u, right? Okay, then this is a constant is 0. So what do you get? 2u, right? 2u. How about this one? We keep the constant v. Very good. Now we do partial derivative with respect to v. So u is constant is 0. We have a negative 2v. So there's 2v, 2v, right? And then we're looking at this one. Oops. Derivative, derivative with respect to v, then u is constant, so we keep the constant. So we have u, right? Okay. Now, 2 by 2 determinant. So we will have, so 2u squared minus plus 2v squared, right? All right. Is it good? Okay, so we have the formula for changing of variable for double integrals here. Okay, so we have a double integration region R, and we have a function, right? So dA. Then we change the variable from xy to uv, and then we have a Jacobian here, and then du dv. All right, so we are using this formula to find double integration. All right, okay, so let's do this problem. So we have this one. Okay, so we want to change it to r and theta. All right, okay, now this is the picture of y equal to 2x x squared, so which is upper semicircle, right? Okay, now we want to find the limit of r first. Okay, so let's do this one for finding r. Okay, so we started with y equal to square root of 2x minus x squared. All right, so we want to find r. We want to square them, both sides. We see what's going on. All right, so we have y squared equal to 2x minus x squared, right? Okay, we move to the x squared other side, so we have x squared plus y squared equal to 2x. Okay, now we can express xy, everything in terms of r and theta, right? So x squared plus r, y squared, which is r squared, right? Equal to 2. X will be r cosine theta, right? So this one and this one, right? Okay, so there will be let's move to the everything left side. So we have r squared equal to 2 r cos, oops, move to the left side. So negative 2r cosine theta equal to 0. Yeah. Okay, we can factor out r minus 2 cosine theta equal to 0. Then r equal to 0, r minus 2 cosine theta equal to 0. Okay, in that case, r equal to 2 cosine theta, right? So we can use the lower limit of r, which is equal to 0. Upper limit will be 2 cosine theta. Make sense? Okay. What about the angle? Yeah. So we found lower, lower limit of or upper limit of r. What about the angle theta? let's take a look, right? So angle theta will be start at 0, right? And then pi over 2, right? So pi over 2. So we can use that. Theta will be between 0 and pi over 2. Between pi over 2. Yeah. Okay. One more thing. We have the equation, right? So function, this one, right? On the top, square root of x squared plus y squared. So let me just write down note here. Another note. So we have a square root x squared plus y squared. So we have inside, which is r squared, which is r, right? Then we can express this one as r. And then we are using Jacobian. So r Jacobian d theta, right? Make sense? Okay, let's do it. So we have theta from 0 to pi over 2 and r equal to 0 to 2 cosine theta. And we have r and the absolute value of Jacobian r theta in that case. And then the r d theta, right? Okay, so we have x equal to r. We have x equal to r cosine theta, y equal to r sine theta. We had the Jacobian earlier, right? So that is the number one, which is r, right? Okay, so we are using that. So we have r from previous example, right? Okay, so there will be theta equal to 0 to pi over 2, r equal to 0 to 2 cosine theta, r times r d theta. Make sense? Okay, so there will be theta equal to 0 to pi over 2, r equal to 0 to 2 cosine theta, r squared r d theta, right? Okay, so we want to integrate with respect to r first. Then we treat theta as constant, right? Okay, so there will be theta equal to 0 to pi over 2 and r to the third power over 3 from 0 to 2 cosine theta d theta, right? Okay, so there will be 1/3 2 cosine theta to the third power d theta, right? Okay, so there will be uh 2 to the third power 8 over 3 cosine cube theta d theta, right? Okay, now we done, right? All right, so next one, we want to integrate with respect to theta, right? But then we cannot do that, this one. So we have to do a little work. Yeah. Okay, so what is the easy way we can integrate? So let's do that. So theta equal to 0 to pi over 2. We knew that we cannot just integrate the cosine to the fourth power over 4, right? We should have a sine, right? Chain rule from here, right? Derivative from here, right? We know that. Okay, so we have 8 over 3, and we can express cosine squared theta, cosine theta, d theta. Yeah. Okay, then cosine theta will be square theta will be, so we have 8 over 3 cosine square theta. We can express 1 minus sine square theta, right? So 1 minus sine square theta, cosine square theta plus sine square theta equal to 1, right? So we have that, and cosine theta d theta. Okay, now we can distribute. So we have cosine theta minus cosine theta sine square theta d theta, right? Okay, so we have a two term. We can integrate that, right? Can you see that? Yeah, we have to recognize whether we can integrate or not, right? So this one we cannot integrate earlier. That's why we convert it, right? In order to make a integration form, right? Okay, so we can split two terms. 8 over 3 cosine theta d theta minus theta equal to 0 to pi over 2 sine squared theta first. I want to write down because we need to integrate that. Okay, now we want to integrate. What's the integral of cosine theta? Sine theta. Good. So 8 over 3 sine theta. And then we want to evaluate 0 to pi over 2. All right. So if we derivative of a sine, we get the cosine, right? So we can integrate by using power rule, right? Make sense? So we will have sine to the third power over 3 over 3. Oh, 8 over 3 missing. Yeah. And then we want to evaluate from 0 to pi over 2. Yeah. Okay. Now, 8 over 3 sine pi over 2. We knew that. I'm going to show you. Minus sine 0, 0, right? Minus 8 over 3. And 9. And sine to the pi over 2 to the third power minus sine 0 to the, yeah. Okay, can you please calculate? So this is 0, right? Sine 0 is 0. Pi over 2, which is 1. So we have 8 over 3 minus 8 over 9, which is common denominator, 16 over 9, which is 1.7777. Okay? Okay, so we have a strategy how to problem solving, right? Changing of variables, sketch the region, XY plane, then write the equation of from the boundary, and then we change it to the variable, then determine the limits, which change it, right? And then using Jacobian, and then integration, and we're using changing the variable when you integrate, right? Okay, so we have this question. So for this, for double integration, so we have x minus y dy dx. All right, we want to change it to uv, and this is a parallelogram, and then vertices there, right? Okay, I brought up one more picture so that we can see that equation easily, right? So basically we connect this line, that is y equal to x plus 1, because we can see that there is a scale, so this will look better. This is a parallelogram, right? So let me just use it here. Okay, so let's take a look, y equal to x plus 1, that line equation, right? Can you see that? Yeah, so y-intercept equal to 1, right? And then slope is to 1. And the orange one, y-intercept is negative 1, slope is to 1. This one, this is the green one here, right? So y-intercept equal to 3. Then the slope is 1 over 3. We can find easily. This one, how to find? We can find, since this is not easy, the y-intercept, I meant fraction, right? It's hard. So we can just using two order pair, right? So one is easy. 1 and 2, 1 and 2, right? And then the y-intercept, which is, this one looks like 1.7 for me. Yeah. So 5 over 3, almost 1.7, right? So 1.6666. So this one use 2.0 and 1.7 and 1 and 2, right? Then we can find the slope, then we can find the equation easily, right? So other equation, very straightforward, right? Okay, now we have all the equation for boundary, right? So for boundary, so we have y equal to x plus 1. Then we can express this one as x. We move to the y other side, and the negative 1 the other side, right? So x minus y equal to negative 1. Okay, we have another one, y equal to x minus 1. So same thing, we can make y is the other side, and negative 1 is the other side. So we have x minus y equal to positive 1 then, right? Okay, now we have another equation. So there will be x plus 9 over 3. So x plus 9 over 3. Okay, so that is the same as y equal to x over 3 plus 9, right? Okay, so we want to make this form, xy form, like earlier. So then there will be, I think, so x is there, y is moving, 9 is moving other side, right? So there will be x over 3 minus y equal to negative 9 then. Yeah. Okay. We don't want the fraction, right? So let's multiply. Wait a minute. We have a 3 there. So 3 there, yeah? So let's multiply by 3. Then we get x minus 3y equal to negative 9. Yeah? Make sense? Okay, so we have that. We do same process of number 1, number 2, number 3, number 4, which is y equal to x plus 5 over 3. So x plus 5. So let's make this way, right? Okay, now we want to make xy form. So x over 3 minus y equal to negative 5 over 3, right? So we don't want the fraction, so we multiply by 3. So we will get x minus y, 3y equal to negative 5. Yes? Okay, now what we are doing, so we want to change it to UV, right? So let u equal to x minus y form. Okay, since we say that x minus y is a u, right? Then u is between negative 1 and positive 1. Can you see that? So u is between negative 1 and positive 1. Yeah. Okay. Let's say that v equal to this form, x minus 3y. Then v is between negative 9 and negative 5. Yeah. Okay. And then let v equal to x minus 3y. Then v is between negative 9 to negative 5. Yeah. Okay. Now we want to change the limit, right? So for finding limit, so this is the limit we will use that, right? So this is the limit. So lower limit, upper limit for u, lower limit, upper limit for v. Yeah. Okay. Now we want to find the Jacobian. So okay. So we have u equal to x minus y. So I am using this one. And v equal to x minus 3y. And then we want to solve for x. And then we want to solve for y. So that we can partial integrate, partial derivative. Partial derivative, yeah? So u equal to x minus y, v equal to x minus 3y, and multiply by negative 3, and solve for x, yeah? So that will be, we have negative 3u equal to negative 3x minus positive 3y, v equal to x minus 3y, yeah? So that will be negative 3u plus v equal to negative 3 plus 1, which is negative 2, right? So negative 2x. Solve for y. So divide by negative 2 both sides. So x equal to 3u plus v over 2, right? Okay, now we have u equal to x minus y, v equal to x minus 3y. Solve for y in the case. Then solve for y. So we will have u minus v equal to negative y minus plus 3y. So It's plus 2y then. Yeah. Okay. Y equal to divide by 2 both sides. We have a 2, right? Okay. Now, oh, you cannot see. So we have T of UV. So we want to make the XY, right? So let me. Okay, so there will be T of UV equal to, we have 3U plus V over 2 and U minus V over 2, right? Okay, so we still need to do Jacobian, right? So Jacobian will be UV equal to, okay, so partial derivative with respect to U, right? In that case, and partial derivative with respect to V. All right, so we consider this is X, this is Y, right? Because we start for X and Y, right? All right, so there will be, can you see that? We're looking at this equation, X equation, and then partial derivative with respect to U. Then the V is constant, right? V is constant. Then what do you get? This is a 0 because another term. So we have a 3 over 2 then. Make sense? So we have a 3 over 2. Okay, take a look this one. We're looking at the y equation with the partial derivative with respect to x. Oh, no, sorry, partial derivative with respect to u. So v is constant, so we have 1 over 2 then. Yeah. Now we're looking at the x, partial derivative with respect to v. Then u is constant, so we get 1/2. Okay, now we're looking at the v and looking at the y with the partial derivative with respect to v, then u is constant, so negative 1/2. Okay, now we do multiply 2 by 2 determinant, so that will be 3 over 2 times negative 1/2 minus 1/2 times 1/2. Yeah. Okay, so we get negative 3/4 minus 1/4 equal to negative 1/4, which is the 1. Yeah. That's why we need the absolute value. We don't want the negative. All right. Yeah, so we don't want the area or volume negative. That's why we take the absolute value for Jacobian to get the positive. All right. Okay. Now let's go back to original problem where we have double integration x minus y dy dx. Then we transformed uv, right? Everything. So x minus y, so we are using x minus y. So x minus y, okay? And we are using du, the limit, negative 1 to positive 1, negative 9 to negative 5. So we did a lot of work, and the integration is much simpler. So we have region R, x minus y, dy, dx. So there will be u first. So u will be, no, u first. So v will be -9 to -5, right? And then u will be -1 to +1. And x minus y. So there will be 3u minus v over 2. This is from the previous. Yeah, this one. And then I'm sorry, uv, everything. Y equal to u minus v over 2, right? Minus, then u minus v over 2. Du dv, right? Okay, now, let's just simplify. V equal to -9 to -5. U equal to -1, U equal to 1. So we have 3u minus u over 2 minus v over 2 plus v over 2. Yeah, because the sign du dv. Okay, so I copied wrong here. So x is 3u plus v, right? So I mentioned that 3u minus, so plus v, plus v. So plus v, then there is a plus v there, right? Okay, so we will get, okay, so I realized that there is a more mistake. Okay, so let me fix that. I'm very sorry about that. Okay, so let's take a look here. Why didn't you tell me? Ooh. Yeah, so here, divide by 2 every term, then that will be negative, isn't it? So that will be negative. Yeah. Okay, then 3u minus v. 3u minus v. Did I make a mistake here? Yes, I made a mistake, right? Okay, so where I made a mistake, the v, right? So let's do one more time. I'm very sorry. Okay, so we want to only x and then v. We need to change that, right? Okay. What's the derivative respect to v? Yeah. Okay, so that will be -1/2. Okay, then multiply and negative. Then 1, negative, negative, positive. So negative 2 over. So negative 2 over 4. Which is -1/2, which is just 1/2. Yeah. Okay. Good thing. Oh my gosh, good thing I found out. It's a negative. Okay, then there will be negative. Then we have a 2 over 2u, right? So that will be So 2 over 2u, which is the u, right? Ooh. So, okay. So let's integrate respect to u. So we have u squared then. U squared over 2. We want to evaluate it from -1 to +1, right? And then the v. So we have v equal to -9 to -5, 1 over 2. Then 1 squared minus -1 squared. Let's just write down. Okay. Then we have v equal to -9 to -5. That's 1. Oh, 0. Yeah, right? Okay, so we get 0, right? So we don't have to do next to, right? So this is 0. And also, I made a mistake again, right? I'm very sorry. So Jacobian 1/2 I did not put there, right? So Jacobian, so open. So this is from Jacobian. Jacobian, right? So Jacobian 1/2, yeah? Sorry about that. Please forgive me. Yeah. So 0. So why this is 0? Because we have a -1, +1. They cancel out each other, right? That's why we get 0, right? We don't have to do that. Yeah. Since u equal to -1, u equal to 1. All right. Okay, so we have a Jacobian determinant for 3 by 3, right? So we know how to do it. Okay, so look, this is what we did earlier, this format, because if we don't have the third one, right? So we had this format earlier, then oops, not this one, yeah. Let me do again, this one. Because we're looking at the x equation, y equation, partial derivative with respect to u, right? And partial derivative with respect to v. But then they say that this is also same. Let's take a look. Can you see that we're looking at the x equation, now y equation, so x with the derivative with respect to u, v, w, right? Can you see that? Slightly different, but it's the same. Okay? Yeah. All right, now we have a triple integration. So we change the variable. Don't forget, we have a Jacobian here, right? Okay, so let's do it. We want to evaluate this one. Remember last section? I had a struggling. I had a struggle or the algebraic work, right? So let's take a look this one. Okay, so we want to use u equal to 2x minus y over 2, v equal to y over 2, w equal to z over 3. Okay, so let's find out this one. This means u equal to 2x over 2, which is x, right? And hold on 1 second. Let us do this one first. I'm sorry, not y. V equal to y over 2. So there will be, solve for y, then y equal to 2v. Yeah? Okay, so there will be, let me do here. So we have 2x minus y equal to 2v. Then over 2. So there will be x minus v. Yeah. Okay. Then we want to solve for x. Then x equal to u plus v. Okay. How about the z here? Solve for z. So we have z equal to 3w, right? Okay. So let me make a table like a book did. So here's a nice picture. Okay, so do I need, yeah, I need more space. Let me use it. Okay. Okay, so we have equation in XYZ. So we have equation in UWZ, right? UWZ, UVW. Ah. And then the limit. The limit is here. Okay, so we have x equal to y over 2. Then we have x equal to, right? So x equal to u plus v, right? Then also, just the first column said y over 2. So y over 2 equal to y was 2v, right? So y equal to 2v. Over 2, which is v. Yeah? Okay. Look, it's corresponding. This is corresponding. U plus v equal to v. U plus v equal to v. Okay. Then we say that u plus v equal to v, then u must be equal to 0. Make sense? Because we say that u plus v equal to v. Yeah? Okay. Then the lower limit u equal to 0 there. And then we have x equal to y over 2 plus 1. Same processing. So u plus v equal to y over 2 plus 1 equal to y over 2, which is 2v. And we have over 2 plus 1, which is v plus 1, right? Okay, now we have u plus v equal to v plus 1. And then corresponding, so v equal to v, then u must be equal to 1, right? Means u must be 1. Yeah, since u plus v equal to v plus 1. V with the same as v, right? Make sense? V equal to v. So we have an upper limit, which is u equal to 1, all right? Okay, we have from the limit. So basically, I did not mention that, huh? So this is x equal to, and this is, I am following same order here, right? So this is y equal to, ooh, y start is 0, and then y start is 0 to 4, x start is 0 to 3, right? Okay, so y equal to 0, then we have v equal to y over 2. So y equal to 0, so we have a 0 over 2, which is 0, right? So limit v equal to 0, y equal to 4, so v equal to y over 4 equal to y equal to 4, so 4 over 2 equal to 2, so v equal to 2. The last one, z equal to 0 to 3. Sorry about that. I made a mistake again. That is not x, that is z, yeah? Crazy. So because I am rushing. This is the last question this way, all right? Okay, so z equal to 0 to 3. So we knew z equal to 3w from the previously solve for z, right? Okay, then z equal to 3w. So that means 0 equal to 3w. That is w equal to 0, right? Okay, z equal to 3 means 3 here equal to 3w. So that is w equal to 1, yeah? So we have a lower limit, w equal to 0, w equal to 1, yeah? Okay, now Jacobian, right? So we do Jacobian u v w equal to, okay, we change it at the form. So xxx over u y, not y, v and w, right? And then y equation, then we have u v w, and then z equation and u v w, right? Okay, so let's take a look. We have x equal to u plus v, right? Y equal to, what was it? 2v, and z equal to 3w, yeah? Okay, now, let's partial derivative with respect to x, y, z, right? Okay. All right, so we're looking at the x, partial derivative with respect to u, it's 1. What about the v? It's 1. What about the w? 0. Yeah? So 1, 1, 0. Okay, let's take a look. Y equation. Partial derivative with respect to u, 0, v, 2, w, 0. Yeah? So we have 0, 2, 0. Yeah? Okay. We're looking at the z equation. Partial derivative with respect to u, 0, v, 0, w, 3. Yeah? So we have a 0, 0, 3. Okay, 3 by 3 determinant. So we make a positive, negative, positive. So we factor out with that. So there will be 1. And then we are using this one. So 2, 0, 0, 3, and negative 1. Then we are using this. So we have a 0, 0, 0, 3, and positive 0. Okay, locally 0. Okay, so we multiply this way. So 6 minus 0, and we multiply this one 0. So everything is 0, right? So which is a 6. All right, now we have this equation. Copy. All right, so okay, now. All right, so let me write down quickly. So we have z equal to 0, z equal to 3. We have y equal to 0, 2, 4. And x equal to y over 2, 2. Y over 2 plus 1. X plus z over 3. dx, dy, dz. Yeah. What was the x? X equal to u plus v. What was the z? Z equal to 3w, right? Okay, so there will be, we change it to the limit 2. So let me write down this one first before I forget. U plus v plus 3w over 3 there, right? And then we want to integrate respect to u, respect to v, respect to w, right? So the first one is u equal to 0 to 1. And second one is v equal to 0 to, let's find out, equal to 2, w equal to 0 to 1, right? All right. So 0 to 2, and w equal to 0 to 1. All right, so we have w equal to 0 to 1, v equal to 0 to 2. All right, so this is a w, and then we do integrate with respect to u. So u is here, u squared over 2. And then don't forget, oh, Jacobian. Oh, Jacobian. Luckily, I remember right now, right? Oh my gosh. Good. Okay. Good thing I remember now. Jacobian was 6. Yeah. Okay. So Jacobian. U, V, W. And then we don't need the absolute value because it's already positive. Okay. So once again, this is a integrate u squared over 2. Integrate this one uv, because constant we keep that, right? And this one w u, right? Because we do integrate respect to u, and w is a constant. Make sense? Okay, now I'm gonna write down 6 Jacobian, right? Okay, so 6, we have u squared over 2 plus v is constant u, and w is constant u, and then u equal to 0 to 1 dv dw, right? Okay, 6 is the Jacobian. Let me write down for now. Okay, now we have w equal to 0 to 1, v equal to 0 to 2, 6. Okay, so substitute, evaluating, not to substitute, 1 over 2 plus v plus W, yeah? Then dv, dw, right? Okay, now let's integrate with respect to v. So 1/2 of v plus v squared over 2 plus wv. Evaluate from v equal to 0 to 2. All right, so that will be 6 1/2, 2 plus 1/2, 2 squared plus w times 2 w, yeah? Okay, now w equal to 0 to 1. So we have a 6. That's 1 plus, that's a 2, 2, so 2 plus 2w, right? Okay, now we have 6, 3 plus 2w, integrate with respect to w. So we have 3w integrate, so we don't need that. 6, 3w plus 2w squared over 2. So evaluate from 0 to 1. Okay, almost. 3 times 1 plus 1 and 0, right? Okay, so we have a 6 times 4, which is 24. Good job. All right. So this is much easier than last section. We had crazy algebraic work, right? So much better. Yeah. Okay. Very simple for the integration, right? Any questions? Thank you for watching. I will see you next time. Bye.